Welcome to a code report solution video. In this video, we're going to be covering the solution to problem number 1 from contest 168 entitled Find Numbers with an Even Number of Digits. The problem states, given an array nums of integers, return how many of them contain an even number of digits. So one of the examples given is the following. We have nums which consists of 5 integers, 12, 345, 2, 6, and 7,896. And the result is 2 because only 2 of these integers contains an even number of digits, those being 12 and 7,896, which contain 2 and 4 digits respectively. The remaining digits all have an odd number of digits, therefore they don't contribute to our final count. So this is a relatively straightforward problem, which I assume most of you don't require this tutorial in order to help you solve. But the purpose of this is going to be to look at a plethora of languages, 8 in total, and show how we can solve this problem a little bit more declaratively using a functional programming style. So the way we would approach this from a functional programming perspective would be to use the 3 primitives map, filter, and reduce. So the first 2 operations we would need to perform are maps, where we're mapping it from first integers to strings, and then from strings to sizes, where the size just is the number of characters in your string, or in other words, the number of digits in our original integers. And then we want to do a filter based on whether or not the sizes are even or odd, and we want to keep the even ones. And then once we have this, we can just do a count or a length of our resulting list of numbers. So to recap, the first 2 operations were maps, the third operation was a filter, and the final operation was a reduce. So across the 8 languages that we're going to look at, Python, C++, Java, Rust, Clojure, Scala, Elixir, and Haskell, here are the names of those algorithms for the map, filter, and reduce. And I'm also including the toString, which we're going to need to use for our first map operation. So for map, every single language calls this map except for C++, which calls this transform. For filter, all of the languages call this filter, which is nice. For our reduction algorithm, which in this case is going to be taking the length or the count, the majority of the languages from Java to Elixir call this count, but Haskell calls this length. C++ has an algorithm in C++24 this called distance, but we're going to hand roll our own in order so that we can use the pipe operator. And Python has len, which is short for length. And finally, the toString methods for Python and Clojure, it's str. For C++, Rust, and Elixir, it's to_string. And for Java, they have a string.value of. And for Haskell, they have show. So let's move on to our code solutions. First, we're going to take a look at 3 different Python solutions. The first one from Python is a non-functional programming style. This is typically what you'll see for beginners who are learning Python. You declare a variable outside of a for loop, which is going to be res for short for result. We initialize this to be 0, so this is going to be the count of our integers that have an even number of digits. Then for each of the numbers in our nums list, we have an if statement that's basically first converting our integer num into a string using the str. Then it's taking the length of that string, and then it's using the modulus operator 2 equals 0 to check whether or not there's an even number of characters in our string. And if we pass this conditional, we do a plus equals 1 to our result. We finish this for loop, and then we return our res variable. So this will work, but it's not the best solution because we are not being very declarative here. Our res variable we're constantly modifying, and only until we're finished our for loop do we actually have the value we want. The second Python solution we're going to look at uses list comprehension, which is a lot more idiomatic for Python. So for here, basically we've got a list comprehension, and then we're taking the length of it. So you can see we have for I in nums, so for each of our integers inside our nums list, if the length of the string of that integer modulus 2 equals 0, then we want to basically include it. So our map is happening here with the len and the stir. Our filter is happening with the %2 modulus 2 equals 0, and then our reduction is happening with our len at the end here. So it's a little bit harder to see that this is sort of a functional programming style, but underneath list comprehension are a lot of the functional programming primitives. And last but not least, we're taking a look at a non-list comprehension sort of functional programming style Python solution. Unfortunately, you don't have the ability to sort of pipe the result of each of your map and filter operations to the next operation, so we have to declare these intermediate sort of lists. Which isn't great, but it still demonstrates how to use sort of the map, the filter, and then our reduction algorithm len at the end. So first we're mapping our integers to strings, then mapping those strings to the sizes using the len, and then we're filtering. This is not really nice in Python. You have to explicitly declare the lambda keyword whenever you want to define an anonymous function or a lambda, which is sort of irritating, but it's what we have to do. So then we do the modulus 2 equals 0, and then after this we convert our intermediate data structure J here to a list and then take the length of it. So that's it for our Python solutions. Moving on to 3 different C++ solutions. Here's the imperative one, similar to the first Python solution, declaring our variable res, setting it equal to 0. We have a C++11 range-based for loop. Once again, converting it to a string using toString, and then converting that to a size using the size method, modulus 2 equals 0, and then we're doing an increment on our variable res here. And then once again, we return it at the end. Of course, similar to the Python solution, this isn't great because we have a variable that we're constantly modifying here. We'd prefer to do something a little bit more declarative. So sticking with C++11, we can use an algorithm called accumulate from the numeric header. Here you can pass it 2 iterators that define our range for nums. And then we can define a binary operator in the form of a lambda here that basically converts each of our integers, which is going to be b, to a string, and then to size, and then do the modulus 2 equals 0. And we can add this to our running total, which is going to be a. And at the end of this call to this algorithm, it's going to return us basically the number of integers with an even number of digits. So this is nice, but it's a bit confusing if you're not familiar with the algorithms. So the third and final C++ solution is the best in my opinion, which is using C++20 ranges. The standard is going to ship this in February, hopefully, or the final ISO meeting is in February, and they'll ship it shortly after. So we're getting basically ranges view transform and ranges view filter. Like I said, we have to hand roll our own reduction algorithm, which we're calling length to be consistent with Haskell. But this now is going to look very similar to our other sort of functional programming solutions. So here inside our map or our transform, we're converting it to a string and then to a size. Then we're filtering for the even number of digits, and then we're reducing this down into the single number, which represents the number of integers that have an even number of digits. Moving on to our Java solution. So in Java 8, we got streams. This enables us to do this kind of functional programming style. So we first just turn our array of integers into a stream, and then we call map, then we call filter, and then we call count. So the remaining of the solutions are going to all follow this kind of idiomatic functional programming solution. Next, I believe, is Rust. Rust is very, very nice. They have map, filter, and count. So these are all going to look very similar from here on out. ToString.len, we filter modulus 2 equals 0. We call .count, but note, count returns a usize, and they have strong typing in Rust, which means you have to cast this to an I32, which is what the answer requires. So you have to do the as I32 at the end in order to get this to compile, which I think is a very nice feature of the language. Next is closure. So this is a modern popular dialect of Lisp. And here we've got map, filter, and count, similar to what we just saw in Rust. So we can use something called threading in order to compose this really nicely and not have to nest our parentheses. So first we do map to string, then map count, which is going to give us the number of characters in our string, filter even question mark. This is sort of nice in closure that all of their predicates, a predicate being a function that returns a Boolean, has a question mark at the end, which I think is a really nice way to read code and to show people which of the functions that you're calling is a predicate. So that's quite nice. And then you just call count at the end. Next is our Scala solution. We make a call to map on our array of integers, and then toString and .length. So we're doing both of our maps at once. And we can actually do our filter and our reduction in the same step here, because arrays in Scala have a count method that takes a predicate and can perform a filter in the reduction at once. So that's kind of nice. Moving on to Elixir. Elixir has map, filter, and count. And at this point, you should be pretty familiar with this pattern: mapping to a string, then mapping the length, filtering based on whether it's even or not, and then making a call to count at the end. And last but not least, we have our Haskell solution, which is, in my opinion, the most beautiful, using dot-free notation. Here you read it from bottom to top, so we're mapping, and we've combined our toString and length at the same time. Then we're filtering based on whether or not it's even, and then we just do a length at the end. So hopefully you found this useful, and I would encourage you in future contests to try and program these solutions more idiomatically in a functional programming style if you can, because in my opinion it's much easier to read. It reduces the amount of mutation you have in your solution, and it's just better in general. And last but not least, we have our time complexity to talk about, and all of the algorithms that you've seen, whether it was the imperative for loop solution or the composition of the map, filter, and reduces, are all linear time. So ultimately, the time complexity of this solution is linear. As always, if you enjoyed this video and found it helpful, hit that like button. If you want to see more, make sure to hit that subscribe button. You can follow me on Twitter for reminders 30 minutes before contests start, and you can find all of the code shown in my videos on my GitHub page. Thanks for watching, and I'll see you in the next video.